The standard model of physics treats mass as an intrinsic bedrock property of matter. An alternative mathematical framework proposes a different origin, that three-dimensional physical states actually emerge from purely lower-dimensional phase interference. Translating abstract phase data into a physical volume requires a specific, continuous mathematical pipeline. This pipeline connects discrete two-dimensional geometry directly to three-dimensional reality. The first step in this process is mapping the behavior of prime numbers onto a strictly defined two-dimensional polar coordinate plane. The second step takes that flat two-dimensional coordinate space and topologically folding it, forcing the data into a bounded three-dimensional boundary. The final step applies directed acoustic resonance within that specific geometric boundary. By trapping intersecting waves, the pressure forces a localized vacuum breakdown, allowing us to synthesize matter. This framework offers a mechanical, testable bridge. It connects the abstract mathematical topology of integers directly to the engineering of tangible physical matter. To build this framework, we need a baseline mathematical grid. The base encoding scheme relies on a discrete polar coordinate array. This animated diagram demonstrates the precise sampling rule governing the grid. For any given radial ring, labeled K, the number of discretization points placed on that ring must equal exactly 3K plus 1. As the rings expand to fill the plane, a unique geometric property emerges from this linear growth rule. Because the node count grows at the exact same rate as the circumference, the grid maintains an asymptotically uniform areal density. The distance between points remains consistent at any scale. If we isolate a single point, we see how the grid functions as a phase encoder. The point's radial distance from the center records its scale, or depth, while its angular position on the ring records its specific phase orientation. With a uniform geometry established, we can transition from a blank grid to plotting actual numeric data. We turn this geometry into an integer phase space. Prime numbers play a specific structural role here. Because primes are multiplicatively irreducible, meaning they cannot be broken down into smaller integer factors, they function mathematically as highly stable phase anchors. To organize these prime anchors, the model utilizes a base metric, a 108-state angular lattice. This diagram shows the sorting mechanism. Primes lock into specific rotational families based on their modulo 13 residue patterns. When we divide a prime by 13, the remainder dictates exactly which of the 13 repeating radial paths it occupies on the 108-node lattice. Applying this modulo 13 metric to the 108-state lattice completely eliminates random distribution noise. The mapped primes visually connect into distinct concentric geometric shells. In this model, prime numbers operate as structured spatial resonances, mapped perfectly on a plane, ready to be projected into a physical volume. A single planar grid exhibits mathematical limitations. A two-dimensional substrate inherently contains representational gaps and cannot encapsulate a full volumetric domain. As more data populates the plane, it reaches encoding saturation. This is a horizon-like boundary where distinct states can no longer be resolved on a flat surface without folding or creating ambiguity. This diagram illustrates the first mechanical step to escape that two-dimensional saturation. We partition the flat circular grid into 3 equal 120-degree sectors. We then execute a topological folding operation. By lifting the central origin along the z-axis, the 3 sectors hinge inward until they form orthogonal, 90-degree corners. The result of this folding operation is a tri-rectangular tetrahedral element. But a single folded element remains mathematically incomplete. It cannot enclose a finite bounded volume on its own. The volumetric solution requires deploying 3 identical, mutually orthogonal folded grids simultaneously. The mapping process brings these elements together. The 3 distinct folded grids move through 3-dimensional space and interlock onto the vertices of a regular tetrahedron. Linear barycentric interpolation flattens the curved 2-dimensional perimeters of the original grids. They snap taut into perfectly straight, 3-dimensional triangular edges, sealing the external boundary. This mutual interference generates the minimal closed 3-dimensional geometric cage, mathematically capable of trapping energy. Inside the sealed tetrahedron, three orthogonal phase fields intersect violently at the absolute center. The emergent particles are not the fields themselves. The localized matter we observe consists entirely of the geometric interference patterns those fields produce. This physical interaction is governed by a strict mathematical rule known as the spatial collapse dynamic, expressed as 3n plus 1 divided by 2. This visualization shows the collapse variables in action. First, the 3n represents the projection of the summed amplitudes of our three orthogonal frequencies. Second, the plus 1 acts as an asymmetric phase shift that prevents perfect destructive interference. Finally, dividing by 2 induces a dyadic contraction, pulling the energy inward to form a stable subharmonic. Physical states only condense at spatial coordinates where the fractional geometric remainder of this operation exceeds a high resonance threshold, specifically greater than 0.94. While a single tetrahedron produces a basic particle, generating heavy elements requires architectural complexity. This is achieved through fractal nesting. A stable core resonance acts as a macroscopic acoustic node. Once locked in place, this central node seeds concentric, lower-frequency standing waves that project outward. These standing waves expand and mathematically lock into successive, higher-order polyhedra, such as a surrounding cuboctahedron. As these nested polyhedra grow in complexity, they approximate the spherical harmonics of the s, p, d, and f electron shells. The original corners of the tetrahedron remain as persistent geometric gaps in these larger polyhedral cages, unfilled channels where energy can be exchanged with neighboring structures. This provides the mechanistic basis for what we observe as chemical valency. Complex atoms and chemical bonds are the predictable results of acoustic standing waves nesting into higher-order polyhedra, exchanging energy and sharing phase states across their geometric gaps. The topological framework doubles as an engineering schematic. We can move from theoretical math to physical mechanics. This schematic outlines the required hardware: 3 highly precise phased acoustic transducer arrays. These 3 arrays must be physically oriented to perfectly replicate the spatial positions of the 3-dimensional synthesized tetrahedral volume. We drive the arrays with precise phase patterns. These patterns are mathematically encoded using the exact spatial Collitz remainder dynamics. The 3 resulting acoustic fields intersect and achieve geometric lock-in within the synthesized boundary. This specific orientation turns the mathematical boundary into a physical constraint. Because the 3 phased arrays synthesize the actual faces of the tetrahedron, the inward driving waves encounter a continuous, reflective boundary with no path for dissipation. The geometry acts as a reflective cage, ensuring that acoustic pressure cannot radiate outward. With the energy entirely trapped, the acoustic density at the focal point increases without bound. The boundless energy eventually forces the local vacuum well beyond the Debye screening length, inducing a localized vacuum breakdown. The concentrated acoustic energy transitions first into visible plasma and finally condenses into stable physical mass.